Well, I want to welcome everybody to our workshop today. My name's Jim Nelson. I'm a professor of hydrology and hydroinformatics at Brigham Young University. This is the second of four workshops organized by the AMS SATMOC team, and we're going to be talking today about extreme hydrometeorological forecasting and flood mapping. And I'm joined by some colleagues. First of all, though, I'd like to express our appreciation to the organizers, particularly, I mean, there's many involved, but particularly Gary McWilliams and Sherry Morris at NESDIS, and also Megan Christensen, who's helped put together the webinar and will be monitoring and helping us out on that end. So thank you to them. And today I'm joined by colleagues. We're going to kind of walk you through three separate segments of our presentation today. First, we'll hear from Sheldon Cusselson, research associate for a cooperative institute and he's at the University of Iowa, but he'll be talking about atmospheric rivers, AR of moisture, satellite observations and applications for heavy precipitation analysis and forecasting. And then we'll move from the meteorological forcings of rainfall to Lyle Prince. He's a master's student here at Brigham Young University, works with me and he will be talking about the GeoGLO's global hydrologic modeling model and the services, and he'll be demonstrating that and showing applications of how we convert heavy rainfall into hydrologic response. And our final presentation will be by Amir Hossein Rostami. He's a PhD research assistant in civil and environmental engineering at the University of Houston. He works with another colleague of mine, Yankee Lee, who's been involved in doing using satellite imagery, satellite data for flood inundation mapping. And Amir Hussein will be talking about forecasting inundation extents with REOF analysis, or FEAR, with GeoGLOS and the U.S. National Water Model. And so we're excited today to present and share this information with you. We'll be monitoring the question and answer. You'll notice on your Zoom link Q&A. And if you have questions you'd like to ask during the presentations, feel free to post your questions there. I'll be monitoring the questions, and if we have time at the end of each presentation, we'll answer some of those questions, and then we'll follow up online as we can during and after the workshop today. With that, I'll also remind you that these presentations will be posted on the website, and there'll be a short survey. I'll provide a link to that at the end of it, and you'll also be getting an email, and we'd ask that you fill that out. And again, we look forward to being with you today and sharing the research and the projects that we've been working on. So with that, I'm going to turn it over to you, Sheldon, and you'll be our first presenter in talking about atmospheric rivers.
Waiting for it. Okay. Thank you, Jim, for that introduction. As a satellite meteorologist working for NOAA NESDIS and now as a researcher for Sierra Colorado State University, I've been analyzing atmospheric rivers of moisture worldwide for more than 3 decades. We knew little about these concentrations of perceptible water moisture before the launch of the first microwave imager on board a low Earth orbiting satellite in 1987. I'm going to tell you as much as I can about these moisture plumes that we now call atmospheric rivers, how we observe them with satellite data, how we try to forecast their precipitation with analysis techniques developed through case studies in the 1990s and refined and expanded in the 21st century with additional new satellite products. Working now with my SERA team, we develop new and update current satellite moisture products with applications so we can better identify and analyze the destructive powers of these atmospheric rivers. By the way, the various satellite products in this title slide are from one of the many atmospheric river events that occurred during the winter of 2018-19 that contributed to the flood inundation on the Mississippi River in March of 2019 that will be talked about in the next session. Let's start with the basics of an atmospheric river, water vapor. So what is water vapor? Water in a gaseous state. To see this water in a gaseous state, we use satellites to sense total precipitable water. And here is a satellite picture of precipitable water across most of the globe, colorized to see different amounts. Next question, what is precipitable water? Answer, the amount of water that can be attained from the surface to the top of the atmosphere if all of the water and water vapor were condensed to a liquid phase. Why then is water vapor important? Well, the answer, if no water vapor, there'd be no clouds made of liquid droplets, no rain falling from those clouds, not much weather or life on Earth, and certainly no atmospheric rivers. What is an atmospheric river of moisture? According to some, it's a flowing column of condensed water vapor in the atmosphere, usually originating in the tropics or subtropics, responsible for producing significant levels of rain and or snow. Tagged on to the end of the statement is especially in the western United States. But as you can see here from the event this past spring, it can produce significant precipitation in other parts of the United States. And I will show you atmospheric river events that have occurred in parts of the globe, other seasons, different ENSO periods that resulted in devastating effects to lives and property from their significant rain and even snow. The other presenters following me, our session, will speak extensively about inundation. To me, inundation can happen not from a single atmospheric river event, but many atmospheric river and even non-atmospheric river related heavy precipitation events over a span of weeks or months, not just centered on the immediate, but affecting areas upstream on tributaries that feed into the inundation area with also their snow melt and weeks or months of heavy precipitation. Since most of the precipitable water in the atmosphere lies between the surface and 3 kilometers, this satellite total precipitable water product is good at delineating atmospheric rivers in the low layer. This satellite TPW classic long fetch atmospheric river of concentrated moisture from the eastern Caribbean to the western Gulf of Mexico and the Mississippi River Valley. The resultant high rainfall amounts are where the atmospheric river cross paths with a number of strong atmospheric disturbances. Internet sites at the bottom of the slide highlight the latest real-time satellite loops of total precipitable water that can help you identify atmospheric rivers across the globe. Even better is an atmospheric river that contains mostly above normal total atmospheric precipitable water values for the time of year based on satellite climatology that stretches back to the late 1980s. In this case, the mostly above normal atmospheric river moisture contributed to making it rain longer and heavier in eastern Texas and western Louisiana, where forcing like a jet stream, frontal boundary, and or upper level forcing mechanism cross paths with the atmospheric river to help squeeze out that higher than normal water vapor. Even better, with one of SERA's newest moisture products, the layer precipitable water, slated to go operational worldwide this summer. This satellite product separates the total precipitable water vapor derived from low Earth orbiting microwave sensor satellites into 4 distinct layers, so we can better see atmospheric rivers at different levels. The 2 lowest layers seen here at the top have their atmospheric rivers aligned nearly together, and we're transporting their long fetch moisture from the Caribbean to the western Gulf of Mexico. At the same time, an atmospheric river at the 700 to 500 hegapascal layer and originating over the tropical Central America was transporting its moisture north and converging with the high amounts of low-level moisture that had been transported from the western Gulf of Mexico. Where these three lowest layer atmospheric rivers converged, even deeper moisture was available to further increase the potential for excessive precipitation. And that's what happened when the disturbance we talked about in the previous slide crossed paths with the now converged atmospheric rivers in the three lowest layers. You might not think an atmospheric river at the 700 to 500 layer, or 3 to 5.5 kilometers above the surface, could contribute much moisture. But we found it can mean the difference between an ordinary heavy precipitation event and an extraordinary, even catastrophic event. That is another reason this additional valuable satellite product has been very useful to our U.S. forecasters for identifying atmospheric rivers at various layers of the atmosphere and increased flood potential. A little history on the importance of satellite imagery, allowing us to first discover and better understand the atmospheric river associated with precipitable water vapor. Before 1987, the only reliable precipitable water information available was from twice-a-day land RAOP stations. Not until the first low Earth orbiting microwave imager was launched in the late 1980s and the GOES sounder in the mid-1990s did we start to see the synoptic atmospheric moisture plumes that we now refer to as atmospheric rivers. A decade since the late 1980s has shown improvement in the way we identify and analyze atmospheric rivers on satellite imagery. As a result, forecasters and researchers are better understanding the different types of atmospheric rivers in all seasons and around the globe. As a result, precipitation and flood forecasts with added model input have improved immensely. And here, I even wrote a microwave satellite applications paper in 1993 that mentioned the easy to recognize satellite signature of a moisture plume, or what we now call an atmospheric river. This was for a December 1992 mid-latitude cyclonic heavy precipitation case that produced heavy rain and flooding along the east coast of the United States and up to 2 feet of snow well inland in the mountains. And here is a better colorized view of the atmospheric river that I analyzed so that I could brief my NOAA National Weather Service forecasters. See those two smaller subtropical atmospheric rivers that converge to form the strong main mid-latitude atmospheric river? The resultant precipitation covered the next 24 hours after the satellite image time of the atmospheric river. And the devastating effects of the atmospheric river to New York City, as reported on the front page of the Washington Post. This example showed the superiority of the low Earth orbiting microwave over the geostationary sensors. Can you tell where the atmospheric river is and where it's causing very heavy rain? Do you know where the moisture plume is coming from? Now, can you tell? This was one of the earliest and best examples of the low Earth orbiting microwave satellite sensor's ability to better see an atmospheric river compared with geostationary water vapor imagery. Why? Two main reasons. The geo water vapor at the time could only see moisture in the upper part of the atmosphere between 700 and 300 hectopascals, while most of the precipitable water in the atmosphere is confined to the low layer between the surface and 700 hectopascals. The second reason also continues to exist today. The microwave can see through the clouds to produce total precipitable water most anywhere. Since geostationary satellite sensors cannot penetrate through the clouds like the microwave, it only provides total precipitable water information where there are little or no clouds. Areas of the globe. Rivers. Here are some impressive looking ones that I analyzed for briefings to forecasters in my country or have talked about in seminars and workshops given to forecasters and researchers outside the United States. As you can see, all atmospheric rivers have a common theme. Their origins are in the tropics or subtropics with their moisture concentrated and extending relatively long distances. As a result, they are usually synoptic scale events. Some of these have two converging atmospheric rivers to reinforce their deep moisture. When they interact with a jet stream, upper level disturbance, boundary and/or orographic area, their moisture is usually squeezed out to produce large amounts of rain that can result in devastating flooding or even disruptive heavy snow or ice if the low levels are cold enough. The South Korea case at the lower right needed the layer simple water product to see the atmospheric rivers originating at the two highest layers over the monsoonal moist northern India. From there, they extended across China and then merged with the two lowest layer atmospheric rivers. The merged atmospheric rivers then extended as even deeper moisture to South Korea and contributed to their excessive rainfall and devastating floods. The atmospheric river moisture transport in this part of the world helps produce the Mayu summer monsoon rainy season in their northern hemisphere summers. Atmospheric rivers associated with tropical systems can originate and stay in the tropics. With these tropical cyclone Irma cases in September of 2017, first affecting Puerto Rico and then Florida, they're associated with Irma's feeder bands. The feeder band atmospheric river produced heavy rainfall ahead of the additional heavy rainfall associated with the center of Hurricane Irma. This would result in high total amounts of rainfall that caused catastrophic flooding in Puerto Rico and then a few days in Florida. In this case, an atmospheric river of moisture from Hurricane Lily's outer band merged with a separate frontal band atmospheric river. The merged atmospheric rivers flowed into the northeast United States and kept dumping very heavy rain for at least 5 days along a very slow-moving front. The result was a large area of greater than 300 millimeters of rainfall and catastrophic flooding. This was also an exceptional case. The convergence of two long-fetch moisture transport atmospheric rivers, one originating far to the east in the middle of the tropical Atlantic, and the other far to the west, originating in the tropical East Pacific, south of Mexico, on the moisture remains of another tropical system. Along with Hurricane Joaquin's moisture off the southeast United States, this laid the foundation for a combined concentrated atmospheric river that began to flow from Joaquin into the southeast United States coast. The state of South Carolina was at the center of it all, and as a result experienced excessive rainfall for the next 2 days that contributed to their devastating 1,000-year flood. In this long fetch above normal moisture from an atmospheric river that stretched from Africa westward to Central America, the transport of moisture kept piling up across Central America. And not just with the total potable water, but within all 4 layers of the potable water, where the accumulated moisture finally met with an easterly wave forcing and the Costa Rican mountains. All that deep moisture was released as a torrential rainfall from thunderstorms that resulted in a few days of devastating flooding. So, as you can see in the tropics, most of the atmospheric rivers are either related to the tropical cyclone or the intertropical convergence zone. Some of the best looking atmospheric rivers stretch and expand across the great oceans of the world, usually during the cooler times of the year. Sometimes an atmospheric river can be seen many days before striking land, as seen with the early start to the winter season along the west coast of the United States in October of 2009. Just the right conditions, with the moisture originating from a late season tropical West Pacific typhoon and a particularly strong mid-latitude jet stream for the time of year, helped this atmospheric river expand across almost the entire Pacific Ocean, reaching the west coast in about 7 days. Fortunately, forecasters had plenty of time to follow the river of moisture hour by hour with satellite information as it crossed the Pacific toward the United States. The public plenty of time to prepare for this unusual early October heavy rain and flooding event. Here's another way of looking at the effects of this intact long-distance atmospheric river once it reached the west coast of the United States. to the end of a very long garden hose, all the way. That is filled and then emptied from the atmosphere's cylinder onto the ground. And even there's an additional shorter, not quite as moist atmospheric river that converges with the main one to help produce the excessive rainfall for this earlier than normal fall flooding centered in California. River of water that originated in the tropical Western Caribbean and resulted in excessive rains and devastating floods on the island of Madeira, just off the northwest African coast. Winter is prime time for these atmospheric rivers because they can be driven by subtropical and polar jet streams that transport the moisture across the ocean, and some can even penetrate into the interior portions of Europe. An analysis of that atmospheric river I did in 2010 for EUMETSAT, the European Satellite Training Agency. The signature atmospheric river aligned with the low-level jet, making for a very efficient transport of deep tropical moisture toward the island of Madeira. A polar and subtropical high-level jet merged over the western Atlantic to form a single, stronger jet that was classically displaced several degrees latitude north of the atmospheric river. Low-level winds parallel the highest moisture usually translates into maximum moisture transport and efficient precipitation production when they encounter one or more forcing mechanisms such as a frontal boundary, upper-level disturbance, jet, and or graphics. In this case, all combined and interacted with the atmospheric river to give record rainfall with devastating flooding effect. From wet atmospheric rivers to white atmospheric rivers. I call atmospheric rivers in the cold season that help produce heavy amounts of snow, atmospheric blizzards. Here are two northern hemisphere moist, long fetch conveyor belt atmospheric snow cases that had their origins in the subtropics within a month of each other in 2012. The one in the eastern hemisphere extended from the tropical West Africa to Moscow, about 9,000 kilometers in distance. The other in the western hemisphere extended from the Western Caribbean to Montreal, about 2,600 kilometers in distance. The Caribbean to Montreal shorter distance atmospheric river generally had higher values of precipitable water vapor than the Africa to Moscow one. Maybe the higher precipitable water, shorter distance, and more direct Caribbean to Montreal atmospheric blizzard helped make Montreal's snowfall greater. Here is probably one of the most long-fetched, moisture-laden Northern Hemisphere winter season atmospheric rivers I've ever seen. From its tropical Eastern Pacific origins, an unusually high concentration of record-breaking precipitable water, even higher than the Montreal case, for the middle of the winter was being transported northeast across southern Mexico, the eastern Gulf of Mexico, and into the mid-latitudes of the east coast of the United States. Did you happen to notice the other atmospheric river feeding into the main one from the east off the Atlantic? That additional moisture would serve to sustain the already abnormally high moisture as it penetrated the very cold air mass, thus helping to produce one of the most extreme amounts of dangerous and destructive snow that would total almost 100 centimeters in the Washington, D.C. area. Atmospheric rivers periodically penetrate the Antarctic and, like seen here, the Arctic region. These atmospheric rivers can bring warmer than normal temperatures that can help produce snowmelt and above normal precipitation, especially during the spring and summer months, and snow and or catastrophic ice during the colder seasons. This recent movie loop of total precipitable water from low Earth orbiting microwave sensor satellites showed the probable contribution of a mid-latitude Atlantic merged atmospheric river just west of the Iberian Peninsula that, when lifted north, helped bring above normal precipitation and temperature to Greenland's east coast and as far north as Norway. I do not know if there's more atmospheric rivers reaching the Arctic or even the Antarctic compared with years ago. But with our ability to more closely monitor their penetration, forecasters and research scientists now have the ability to keep track of their effects in that region of the world during these times of changing climate. So that you can follow atmospheric rivers around the world each day, even hour by hour, here are some internet sites that have the latest real-time satellite images and loops for total possible water and layer possible water. Hope you check them. Hope you can check them out wherever you live. I've listed my email address and encourage you to communicate any questions about anything I presented today, including these satellite moisture products that can be very helpful in analyzing and forecasting atmospheric rivers worldwide. As I conclude with the next two slides, an individual atmospheric river usually does not remain over a particular area for more than 24 hours. Yes, it can result in heavy amounts of precipitation that can result in localized flooding that disrupts people's lives, but it usually does not result in widespread catastrophic flooding or inundation to an area unless many atmospheric rivers affect the same general area in the recent weeks or months. These are the individual atmospheric river events, 16 in all, seen by the satellite total possible water between February 12th and March 16th of 2014 during this ENSO neutral winter. They all occurred before a long-term area-wide inundation flood and unexpected March 22nd deadly landslide that occurred from the previous atmospheric river storms that affected the U.S. Pacific Northwest. Keep that thought as the next slide will lead us into our next set of talks. Finally, the El Nino winter of 2018-19, at least 10 atmospheric river events from December through February affected the Mississippi River area and will be talked about, hopefully in the following session. The total precipitable water on the left, a good proxy for low-level moisture, showed those atmospheric rivers mostly originating from the tropics east and south of the Mississippi River area. The 700 to 500 hectopascal layer precipitable water provided us with a better ability to see higher layer atmospheric river moisture, usually from the tropical East Pacific, and after making it over the Mexican high plateau in many of the cases, combined with the low-level total precipitable water to result in heavier precipitation for most of these events. Still, my main overall point here is that one atmospheric river event can result in very heavy precipitation and even localized flash flooding or even heavy amounts of snow, but it usually takes weeks, maybe even months of these atmospheric rivers at different layers and tropical origins to produce the kind of inundation that we talked about by our next speakers. El Nino winters like 2018-19 in this part of the United States usually produce lots of atmospheric river heavy precipitation events in the Mississippi River Valley that have correlated well with low-level connection to the tropical Gulf of Mexico, Atlantic, and or Caribbean, and a connection to the tropical East Pacific Ocean in the higher layers. And that is what happened with most of these 10 events leading up to the additional heavy rainfall during the spring of 2019 that resulted in the worst flooding in over 90 years on the Mississippi River. Uh, the
So Sheldon, I don't know, this is Jim. I don't know if you can access the Q&A, but there's a few questions there I think you have time to respond to.
Okay.
Um, it might be easier to find them if you stop sharing your screen.
Oh,
And I think we have time for you to answer a few of those questions live if you would like to.
or okay, okay. Yes, well, let me answer about the temporal resolution. Yes, the temporal resolution. That's why I always um, explain to teachers that um, the satellite data is not enough. Looking at the whole picture, satellite data, both geostationary and um, that um, uh, they both have their positives, and so that since we don't have a microwave on the geostationary satellite, um, that's the unfortunate about not being able to see what's underneath the clouds. So you are right about the temporal resolution, but the aspects of the microwave should be included in any forecast, and by looking at these atmospheric river that are around the globe. Okay, is there any distinguished?
Why don't you go ahead and read the question, then before you respond, that way it'll be fresh for everybody.
Okay. One question that says, is there any way to distinguish an atmospheric river from phenomenon that are also caused by moisture convergence, etc., like storm formation, jet streams, etc.? Oh, usually your atmospheric
Sheldon?
over the great oceans, usually the atmosphere, yeah.
Yeah, can you
Oh,
get closer to your
usually the
monitor so we
atmosphere.
can hear you better? Your
Oh,
voice is breaking up.
can you hear me now?
Go ahead.
Oh, yeah. The question is also vapor convergence. Concrete mathematical ways to define an atmospheric river. Well, um, I I just look at it as a concentration of high amounts of moisture that are together and long and have a subtropical or tropical origin. And at the end of that atmospheric river, if there's a forcing mechanism like a jet or a which you can see in geostationary data with the various um, uh, upper level water vapor images from the geostationary images. Um, use that to see how it interacts with the atmospheric river that you see with the microwave, mostly microwave data. Um, um, you know, you have to use both to get a better idea of analyzing the weather on satellite data. But one question I don't understand really answer it. It says forests, water, and people in the humid tropics, past, present, and future hydrological research for integrated land and water management. Um, I don't know whether that's a question or not, but um, I pretty much was just presenting on satellite atmospheric rivers that you can see with satellite data and special satellite data like the microwave instrument on polar orbiting satellites. Let's see. Uh, what is the relationship between atmospheric pressure and atmospheric river? Never really thought about that. I don't think there's a whole lot of relation between atmospheric pressure and atmospheric river. Atmospheric river is a concentration of moisture. Atmospheric pressure is just the pressure at a particular level of the atmosphere. You could have them if you have them overlay. If you have strong low-level atmospheric pressure overlaid on an atmospheric river, I'd say watch out for the heavy precipitation that's heading your way. That's about the best I can do with an atmospheric pressure atmospheric river relationship. Okay, and somebody asked about atmospheric blizzards. Well, that's um, that's something I made up. You probably don't ever hear about atmospheric blizzards, but um, if you've got atmospheric rivers and they talk about atmospheric rivers and they go right into the coldest air during the winter season, both in the northern hemisphere and the southern hemisphere in their respective winter seasons, then you can have extremely heavy amounts of snow, especially if you have orographic lift and any kind of disturbance that's forcing that moisture out of the atmospheric blizzard, the concentration of fine moisture. And how do you assess water is turning into snow, hail, rainfall, fog? Well, that you have to look at the various variables, the surface map, even the low-level soundings that are around. Um, uh, you don't just look at an atmospheric river and say it's going to be snow or rain. You have to look at other stuff that's going on both at the surface and the levels near the surface to assess whether you're going to have a catastrophic ice event with this atmospheric river, or a catastrophic snow event, or even a catastrophic heavy precipitation event with the atmospheric river during the winter season. So all of the meteorological variables and in the context of also looking at all your different types of satellite data to come up with assessing whether that water plume or atmospheric blizzard is going to cause snow or melt away into rainfall. Somebody asked about the characteristics of several monsoonal systems in the atmosphere. Okay, well, in the Western Hemisphere, we have the North American monsoon, which affects mostly the Southwest United States, but in the higher levels can extend all the way across our United States and contribute to high moisture to heavy convective precipitation events during the United States summers. Well, at this time of year and through most of the summer, the the same kind of deal occurs in the Eastern Hemisphere with the Maivu monsoonal system that has usually has a concentrated high area of moisture that comes from Southeast Asia or just off the Southeast Asia coast up toward Japan and Korea, and merges with the higher layer level moisture that's spun off from the Indian monsoon. And I kind of showed that with the South Korea case from last year in 2023 that caused exceptional heavy rainfall from a slow-moving frontal system that was moving through South Korea that produced devastating flooding. A variable that can be projected for future periods according to SSPs. I'm not really sure what SSP means, but the numerical models do a good job, pretty good job with these atmospheric river events and water vapor, maybe forecasting the short term. But you really need to kind of monitor these atmospheric rivers, not only day by day, but hour by hour as they approach your area, if they are in your area. And you can even try to project them toward your area and their effects on the particular area. In this case, right now in the Eastern Hemisphere, you have a nice atmospheric river from just off the southeast um, Vietnam coasts on up into just off the China coast and toward the southern Japan. That's merging with higher level moisture to kind of deepen the atmospheric moisture over southern and southwestern Japan. That's probably going to result in extremely heavy rainfall and maybe even some flooding for the next few days. A frontal band atmospheric river. Well, the atmospheric river with a frontal band pretty much aligns itself pretty much parallel to the frontal band, and the feeder band atmospheric river pretty much aligns itself parallel or right on with the feeder band of the tropical cyclone. Both can be very can be extremely heavy rain, produce heavy rain events because the frontal band there's a lot of convergence along the front, and the feeder band has a long stretch of moisture that keeps training over a certain area and keeps feeding into a particular area ahead of the extremely heavy rainfall with the center of a tropical cyclone. So both can be very deadly in the way of producing heavy precipitation, heavy rainfall, and flooding, and even catastrophic flooding. Okay, somebody mentioned, thank you for your presentation. I've seen some studies that atmosphere using integrated water vapor transport. Yes, a lot on integrated water vapor transport, and if you Google Marty Ralph, you'll maybe find his webpage from the Scripps Institute in California that actually puts out model integrated water vapor transport. And that's extremely important. I tried to emphasize in my talk that the winds parallel the highest moisture produces very, very high integrated water vapor transport. And product that we're developing satellite-wise, vapor transport, not just total vapor transport, but layer vapor transport, so that we can get close into where exactly the heaviest rainfall is going to fall that can produce the worst flooding in a particular area. So there's they are kind of a little different. An atmospheric river of moisture with it, the total of water. But if the winds are not blowing nearly or exactly parallel the highest moisture, they're not really going to produce the type of integrated water vapor transport that you want to see for an exceptional heavy rain event. Okay, somebody asked the question, can you explain an atmospheric river on the monsoon system? Well, they impact the monsoon system of the North American monsoon because these atmospheric rivers connect up as far away as the Western Gulf of Mexico, the Eastern Tropical Pacific, and they drew all their moisture northward into the southwest part of the United States. And it's a big reason why there's usually big rainfall events in the southwest part of the United States, where they get most of their rainfall during this time of the year, and is important, just like it's important for the monsoonal system in India to get going with their atmospheric rivers. I read an article that said that 70% of the atmospheric rivers, 70% of the heavy precipitation with the Indian monsoon are related to atmospheric rivers. Now they may be shorter, but if you look today, I looked today at the precipitable water over the Indian Ocean. The there's an atmospheric river that originates just off the African coast and extends into India. So that could be an important factor in producing excessive amounts of rain in the coming days across at least western part of India. All that hooks up in the high levels over northern India, which gets forced east and northeastward across China and into either Korea or Japan to add to the high moisture over the Western Pacific that produces the exceptional rainfall at this time of year there. Live demo river. I'm not sure I understand that. More than welcome to send me an email if you can describe it a little bit better. Especially if you could tell me where you're located, and I can look at different products. You get many atmospheric river events. Hey, how do you consider ENSO while simulating extreme flooding events in the region climate model? Well, that's kind of out of my expertise because I was mostly an analyst, satellite analyst that helped forecasters understand how to use satellite data in forecasting different extreme events. So these atmospheric rivers occur in any ENSO period. Doesn't matter whether it's La Nina, El Nino, neutral. You have atmospheric rivers going on every single day of the year. You have many different ones. In the Eastern Hemisphere, you have one that's extending from the tropics toward New Zealand right now. You have one, as I mentioned, extending from just off the African coast toward India. That's associated probably with their monsoonal moisture. And you have a real well-defined one that starts in the high levels of northern India and extends across China into southern Japan. So are identifying those areas now, and one question: do we use TPW and integrated water vapor transport to detect atmospheric rivers? So, well, if you look at them separately, yes. If you look at the total potential water separately, yes. They kind of go hand in hand. An atmospheric river, as I said, that it has a very high content of integrated water vapor transport will usually mean an extreme amount of precipitation at the end of the atmospheric river of total potential water. So hopefully I answered that question. Uncertainties in measuring and understanding an atmospheric river. Well, the most uncertainties are not having enough satellites to detect them. The person a number of minutes ago mentioned about the latency of polar orbiting, low Earth orbiting satellites, not having enough of them to measure these atmospheric rivers constantly. What we've had to do is infect the moisture till we get a new satellite image. So that that's kind of probably the big hang up with seeing them real well. The latency of a particular satellite. But in the coming years, with small satellites being launched, we should be able to monitor these atmospheric rivers better with in the microwave. Because we're not going to have a microwave on a geostationary satellite. And the microwave sees the atmospheric river better because it sees through the clouds and comes up with the total amount of moisture with the particular atmospheric river. Possible to identify the atmospheric river from satellite data. Well, well, the way I look at it, total atmospheric moisture, a atmospheric river of total precipitable water, since most of the moisture in the atmosphere is below 700 hectopascals or below 10,000 feet or 3.3 kilometers. That's about as good as we can do about identifying the altitude of the atmospheric river. Now, that's the reason why we included the layer precipitable water so that we could see the precipitable water at 4 distinct layers of the atmosphere: surface to 850, 850 to 700 hectopascals, 700 to 500, and even the 500 to 300 hectopascals. So we can identify, sometimes we can identify atmospheric rivers at all 4 of those layers, and if they're aligned all together, their moisture is being transported toward a particular region, I'd say look out for extremely heavy precipitation and localized flooding. When I was talking and briefing with the forecasters who were out there, heavy precipitation events. Thank you, sir, for your presentation. My query isn't to rely a question, rather it's related to asking your opinion based on your experience. Do you believe that the ENSO cycle are the results of climate change, or they are transition climatic variability, self-adjustment to local climate systems? That is a loaded question. I know the climate is changing. There are some strange parts of the world where the climate is getting warmer, and we're seeing it with the glaciers melting, especially in the northern latitudes in the northern hemisphere and the southern latitudes in the southern hemisphere. But I don't know. I think you have to continue to be questioning the climate change in all parts of the world. Some places it may be changing more than the others, but at least for atmospheric rivers, there's been not a whole lot of change that I can see over the years. And I've been looking at atmospheric rivers since the microwave age of the late 1980s, early 1990s. I think my group has a climate proposal, and hopefully maybe we can answer that, or try to answer that question with the amount of precipitable water data that now goes back to the late 1980s to see whether there are local climatic changes going on, at least with water vapor.
Sheldon, why don't you answer one more? I think it's actually the next question is a really good lead into the other 2 presentations, and then we'll move forward.
Okay. Yeah. Do you know? How ENSO events impact the frequency and intensification of atmospheric rivers. Namely, have you explored the ENSO mode differences? Central Pacific, East Pacific, ENSO events for both La Nina and El Nino. Unfortunately, no, I haven't done that. Not really part of my research. I think there are other people that are more qualified doing kind of research on that. I will tell you that atmospheric rivers, like I said, occur at all ENSO cycles. Now, they may be more frequent in certain areas, like in my region, in the United States. They're probably more frequent in Southern California area during El Nino winters, more frequent during La Nina in the northwestern part of the United States, and maybe a little bit in between there with neutral conditions. But as I said in my talk, during El Nino years, there's usually a connection of atmospheric rivers from the tropical East Pacific into the southern part of my United States, from the high levels and the low levels from the either the Atlantic, the Caribbean, or Gulf of Mexico, which makes for more precipitation in the El Ninos in the southern part of my United States. But
Hey, so Sheldon,
where
the
the
question
atmosphere goes on. Yeah.
question I hoped you might answer, it's from Jarson Sokosa, and he says, how can you forecast the extent an atmospheric river can span to predict impact areas?
Guess I don't see that.
It's
Yeah. Do you have a timestamp?
it's 11:39 from Jarson Sokosa.
Oh, in PMs.
No, it's 11:39 a.m.
Well,
Anyway, the question is, how can you forecast the extent an atmospheric river will impact? And I think that will be a good transition to the next talks. But
okay. The length of the atmospheric river, the amount of precipitable water in the atmospheric river, the concentration of the atmospheric river, not so much that it's a large atmospheric river width-wise, but it can be very concentrated, and with the winds parallel the highest moisture. The stronger the wind, the better. Through that atmospheric river. At the end of that atmospheric river, you're going to have an extremely amount of moisture transport that when it hits that frontal boundary, that upper level disturbance, that orographic location like we've seen in California and the western part of the United States, then you really know that's going to be an extremely important heavy precipitation event from that atmospheric river. And satellite, we see that in the satellite, every hour with images, and we can kind of track that very well. And with model input, it helps increase our confidence in how to forecast them.
well, thank you. I appreciate that, and maybe
I hope
very excellent presentation. Helped me understand atmospheric rivers a lot better, and I hope everybody else that's joined. And maybe if you want, you can give Sheldon a big hand from virtually from Zoom. You'll see the opportunity to provide a reaction, and we'll thank you, Sheldon. And we're now going to move on to Lyle Prince. Lyle is going to talk about now global hydrologic model. So how do we take this precipitable water, the forecast, meteorological forecast for precipitation, and use the tools, the GeoGlows tools, in order to get a response hydrologically on the ground. And so, Lyle, I'll go ahead and turn it over to you.
Thank you, Dr. Nelson. We'll go ahead and get the screen share going here.
And Lyle, I'm going to mark your questions that you answered done, but you might continue to type answers or follow up on those later ones that you didn't have a chance.
See where. Let's see. Okay, is that screen share coming through correctly?
You'll want to swap screens at the top. We're seeing the speakers. There you go.
Now you're seeing the right thing.
Yeah, but it's small. I don't know if you can share directly the application because
Let me flip this. I don't know why it's being.
now swap again.
Say. Okay,
There you
now
go.
there we go.
That's better.
Perfect. Well, So, as Dr. Nelson said, I'm going to be talking about global hydrologic modeling and how we can provide global information to local decision makers and help them make informed responses to some of these hydrologic events that are, of course, driven by the meteorology and the meteorologic events that we've been discussing so far. Specifically, we'll be talking about the GEO Group on Earth Observations initiative. They're a partnership of more than 100 different government agencies and participating organizations that envision a future where decisions and actions for the benefit of humankind are informed by coordinated, comprehensive, and sustained Earth observations. So they help with the Earth observation side, which includes satellites, of course, and other observations that help get us better information. And in terms of water, they have their Global Water Sustainability Initiative, which is headed up by Dr. Angelica Gutierrez from NOAA and the U.S. Office of Water Prediction. It's a initiative to help understand better the global water supply, help understand how it works, and connect people with this information so that they can have sustainable practices and can really thrive. So how does the GeoGlows work? What is it? The idea is to connect people with the information and to make global hydrological predictions and then get them to people. So it's got a variety of organizations that are involved in collecting the data and in creating the models and sharing them. NASA, NOAA, ECMWF, BYU, and others we'll talk about as they come up, and is partnered with the NASA Severe program, NASA Water Resources, and then the NOAA and NASA satellites that provide information for flood mapping. Over here on the right, we could see that in order to help with global water sustainability, not only do you need actionable data, information, and knowledge, you also need to help the users meet their needs. So it also, instead of just providing information, the GeoGlows initiative also helps with developing the capacity of local users to respond, to help them be more knowledgeable, and then to really help fill their specific needs, which vary widely across the different regions of the globe. Together with this, the Severe has helped a lot in helping to connect GeoGlows to specific users that have needs around the world, helping to aid this resilience in weather and food, helping prevent disasters and monitoring land change, all of which, are of different levels of importance in different areas. And their goal is to connect space to village, which is kind of the idea of let's take this information from these satellites, these observations, and let's get it into a form that people can understand, people can use, and make informed decisions. So in order to do that, you've got to take the hydrologic cycle and find a way to predict it and to model it. And the hydrologic cycle is very complex. There's a lot of things that go on. We've kind of talked about some of the stuff that goes on while water vapor is in the air. There's a number of other things that happen to it as it rains, runs off, soaks into the ground. And it's very complicated, and it doesn't, the exact ways it works depends on the lands it's hitting, the different regions, temperature. There's a whole lot of variables that affect the hydrologic cycle. So one of the ways that we can address this complexity is through improving our water intelligence. Now, our understanding of the hydrologic system is incomplete. When that is incomplete, people make uninformed decisions. And the goal of GeoGlows is to provide better solutions. If you could know for certain the flow of every river, or even an estimate of every river in the world ahead of time, that really changes your local applications. It really helps you adapt to things that are coming because you're informed before they get there. So in order to try to address the lack of knowledge of our of the hydrologic cycle, there's a lot of monitoring stations that have been established. We've focusing today on remote sensing on satellite data, and we've talked about meteorology. Other important information includes soil, water, groundwater, the rainfall amounts and locations, and then water quality. And all of these help to understand the hydrologic cycle and are great. The only problem is all of these methods are expensive. They're not available globally. Even if data exists in certain countries, a lot of times that data is reserved within the country and is not shared. So that creates difficulties in understanding how the full global system works and how it operates. So in order to leverage all of this data, it's also large, and the data on it it's sitting there doing, if it's just sitting there, it doesn't help provide any actions, doesn't help improve our response time. So through cloud computing, we're able to leverage the advances in Earth observations and connect them to the meteorological services, to governments, NGOs, and geo partners to help them make the decisions that they need to make. So what is the actionable intelligence and hydrologic modeling? So as we've kind of talked about, hydrologic modeling has to, in some way, help us understand where the water's going and what it's doing. We can see, you know, we've got precipitation, you've got all of these different things that you need to model. Once you have a hydrologic model, it can help you understand patterns, trends, and changes in the water cycle. If something, you know, if there's seasonal flows that happen every year, you can begin to understand that, if they're getting better, if they're getting worse, how things are changing. And that helps you understand what things are going to be like in the future, how it's going to be different, which leads us into predicting. You know, a good hydrologic model can predict where, when, and how much water you're going to have, which is important both in terms of flood prevention, in terms of drought and providing enough water. It's very good to know what's coming so that you're able to manage your watershed in a more sustainable way. So the goal is that you can identify, you know, when different threats or flows are coming, you can create a plan to deal with them and then respond in a way that mitigates the impacts and enables good responses. So that all can be very difficult to do. Hydrologic modeling is expensive, it's time consuming, and it requires a certain level of expertise in order to make a useful model. And the way it's worked many times in the past is agencies collect land use, they collect meteorology, they have all of this wonderful satellite data, and they make it available globally, which is great. And then all of this information is passed to the local areas, where every local area that wants to know what's going on needs to make their own hydrologic model. They need to calibrate it, they need to understand it, they need to get all the data, and then they can pass it on to the local governments and the decision makers. The difference that GeoGlows makes is they try to move this hydrologic modeling system to something that is done globally and then provided to the end. So many projects have helped people establish hydrologic models. When the project is done, a lot of these have fallen into disrepair or due to lack of understanding or funding or computational resources. So by moving this over to a global model, it enables the decision makers to receive information about where the water will be and when, which is something they can understand and act on instead of having to go through all these other steps. Now, a global model, for anyone who's familiar with hydrologic modeling, normally you're trying to do these very small scale things. So a global model does have some limitations in the accuracy that it can provide. Similar to, these old satellite images. This example of Google Earth imagery from 1985, it's really hard to tell what's going on. But as time has continued and as things have gotten better, we start to see that this image is a little clearer and a little better to help us understand what's happening on the ground. And of course, that's continued to improve. I mean, this is the same area through the years. Now we're able to see individual streets and houses, and through Google Earth, we can even get 3D images and can walk around the different streets. And as it's improved over time, it's helped everyone. With the global modeling, a similar pattern, over time, as the data gets better, we're able to leverage that data, and it will improve and become more actionable and higher resolution for all of the globe. GeoGlows helps to overcome 4 specific global modeling barriers. The first problem is big data. What that means is there's so much information from all the satellites, from all the monitoring systems, that if you were to try and gather it all yourself and use it all on local computers, it would be very difficult, very slow, and infeasible. So GeoGlows has helped to develop cyber infrastructure and workflows that enable the data to live in the cloud, to be used in the cloud, and got computation resources that process the large amounts of computation that's required to produce a global hydrologic model. Once that's completed, the second thing is you've got an answer, you've got a hydrologic model, you have to get it to the users. You have to be able to communicate this message in a way that makes sense, in a way that's quick, in a way that's easy to understand, and can be used. So GeoGlows has a number of web apps and web services. We'll look at some of those a little bit later in this presentation that help anyone in the globe to be able to see the forecast and understand it, but also the web apps can be customized for area specific needs, which helps them with adoption. Just because information is available and it's there does not mean people will use it. So GeoGlows has a number of partnerships that reach out and help to provide trainings, to provide collaborations, and help every area understand and be able to get this information and get it used. And then, of course, back on the scientist side, there's an ongoing process of improving the model, validating it, correcting it, and continuing to improve the forecasts that we're making. So now that we kind of understand the big picture of what GeoGlows seeks to do, we're going to hop in and look at how it works a little bit. So the way it starts is you've got the meteorological forecast, and we've talked about that with Sheldon's presentation. Now we need some way to translate this to the Earth. So GeoGlows uses the ECMWF land surface model. And the way it works is it takes this meteorological forecast, it's got a grid. Inside that grid, it simulates precipitation, evaporation, snow, infiltration, all of these hydrologic processes, and gives a runoff depth, which is the amount of water for every grid cell that is going to exit. So we can see it gives us the runoff grids here. But the runoff grids, they're locked. Water cannot exit a runoff grid. So in order to understand how the water is getting out of the watershed, we need to understand something about the watershed. A watershed is a area that all the water that lands in a certain area makes it to a stream. And so we've got a global set of catchments and streams where every spot we know what river or stream that should go to, and then we know which river connects to which. So by overlaying these, we can see, oh, everything from these cells will eventually drain to this point. So we're able to translate that runoff depth into a flow. And once water is in the stream, it's then routed down. You can see here there are many different catchments that all converge through a process known as Muskingum routing, which is a method of representing the travel time of water and how it spreads out as it travels down a river. If you've got a big flow, the further down it gets, it's going to spread out. It's called attenuation. It can vary from river to river. If you can get that correct, you can model your travel times so that as the rain is passing over, you're able to predict where the water will be, how long it will take to get to a certain point. And so this is kind of an overview of the process. All of this stuff is happening. Taking the ECMWF forecast is happening on large computers all in the cloud. The results from that global model, which provide the information, is then going into different web services. There's Streamflow API. You're able to go to any area in the world, look at all the forecasts and the historical data, and then that can also be integrated with custom web apps, which we'll talk about. So really, now that you've got all those systems in place, you're taking the meteorology data, you're getting it into flow data, and you've got a web app, you're able to provide actual information. And then the last step we've talked about is adoption. So we're going to kind of look through some examples of adoption and ways that GeoGlows has been used in the global scale. So we'll look at that, and then we'll kind of delve a little bit more into what exactly you can get. So one of our first examples, this is was in Malawi. They had a community-based early warning system for floods that only had a lead time of several hours. By taking the forecasted flows from GeoGlows, which extend to 15 days, they were able to greatly extend their lead time, which is vital in responding to flooding events. During the 2022 flooding season, they were able to implement this, and during that season, not a single life was lost. Whereas during a typical flooding season, tens to hundreds of lives are lost. Their government also estimated a savings of $40 million in damages. In Israel, they were able to build themselves a custom app and able to integrate the GeoGlows forecast into their system, able to pair it up with several stations in Israel and Gaza and provide better information. Honduras has been able to use GeoGlows to forecast their water, which help them manage reservoir releases during back-to-back hurricanes. You can kind of see on this graph here 2 large spikes in the amount of water that was coming down the river. The first hurricane pretty much filled the reservoir. They were worried about reservoir failure, which would have created catastrophic flooding downstream. But by being able to see the second huge spike in runoff that was coming, they were able to open the reservoirs and release a lot of water in those days that they had, which did cause some smaller flooding, but mitigated the potential for a much larger disaster. In Guatemala, they've been able to integrate it similarly with hurricanes to understand the risk for where flooding could occur and to provide hurricane warnings earlier than their other systems. In Nepal, they've been able to use the forecasts. They've found them to work very well, and they've been able to supplement the other data and models that they have. It's been able, as their director says, has the real possibility of saving lives and property as they've understood better their watershed. In Bangladesh, 92% of their watershed areas lie outside the country, and that's data that's not necessarily available to them because GeoGlows is a global model. It's been able to fill the need of that transboundary data, helping them understand what's going to be coming into their country so that they can understand the water they're going to have, and has helped increase their understanding. The Dominican Republic has been able to adopt GeoGlows, and it provides a benefit that they previously were not able to have, that has helped them quite a bit with their water supply for irrigation, with flooding, and with reservoir operations. In severe Amnesia, they've been able to help many countries. They've had 28 capacity building workshops, trained more than 300 people in the last 3 years. So that's a lot of, this is kind of more on the capacity building side, helping locals understand and make better decisions. In Colombia, obviously the Amazon jungle is a very difficult place to monitor and put gauging stations. GeoGlows has been able to help provide information in those areas and help kind of patch the holes in their understanding of those areas. Ecuador is kind of has been involved a lot. They've got their very own portal, kind of a great example of how they could been able to customize the GeoGlows information to the exact applications that they've wanted to have, and it's providing a lot of great information to their various stakeholders. And you can see here screenshots from their customized apps that they've been able to build. In Peru, they've also integrated it with their local model. It's helped fill in gaps. You can see they've got alerts for their flooding. It's been helpful. Similarly, in Brazil, it's been used to provide disaster warnings. They also have a lot of area in the Amazon that it helps to model, help them understand. You can see there some of their warnings. So as we can see, GeoGlows has a lot of applications. It's been used in a lot of places. We're going to look a little bit at the customization. So inside a program called Tethys, you can build these web apps that link right with the GeoGlows data. And besides just providing stream flow, there are other applications that can also include groundwater and different information from some satellites and help you explore what's available. All these apps can be customized and put in a portal. It's similar to how on your phone you can go and get, whatever apps people have made. Once these apps are created, they can be shared and help many different people receive the information. You can see different countries here have created their own apps that they can use and then be placed in their toolbox and help understand this data. So this app nursery has been greatly helped by AWS, Amazon Web Services, for supplying the storage and had kind of the backing to make all of this possible. And you can see some different app toolboxes that have been created to meet the needs of different countries and different people. So let's take a little bit closer look now at the GeoGlows data, what it is, how it works, and we will hop in to see some of the data in real time. So this is just an overview again. We're going to look now at these web services and the stuff you can get and the stream viewer. So right now, GeoGlows is in the midst of transitioning from its first version to its second version. There's some details here about the differences between the two. And there'll be links to both of the stream viewers. On the next slide, the biggest difference is that from GeoGlows 1 to 2, the resolution jumps up a lot from 1 million streams to 7 million streams. It's broken out a lot finer, has a longer period that it runs. And so we've got these two Hydro viewers. This right now, the version 1 Hydro viewer is live at apps.geoglows.org. The version 2 Hydro viewer is what we'll be using today. It will soon be replacing the version 1 Hydro viewer at this link. It's still in beta, but it provides more reaches. We'll look at that. So I'm going to go over quickly some of the information we can see on there, and then we will hop into a live demo. The main thing that you're going to see on there is the forecast. As mentioned, it's got a 15-day lead time, so you can see, like in this example, we're back here and we're able to see, you know, in 2 weeks we're going to have some water coming, so you can kind of prepare for that. The statistics show uncertainty bounds of all the different forecasts, which can also be viewed as ensembles. So really the ECMWF forecast has 51 different ensemble members. GeoGlows routes all of them through its network, and each ensemble then corresponds to a different line. So you can see some models are predicting for this flood that it'll peak sooner, some are predicting that it'll peak later, and of course, as it gets closer to the present, they all tend to agree a lot better on what's going to happen. And then one important thing that is used commonly in hydrology to understand the seriousness of a flow are return periods. They're used to classify extreme events, and they're a statistical based method that basically looks at the record over the river and says, okay, the biggest flood should only occur about once every 100 years. So we see over here return periods 100 year. That's this purple zone. That's saying statistically, the exceedance probability means that this should happen once every year or once every 100 years. Now, because it's not a guarantee, it doesn't mean that it will only happen once every 100 years. You can see in this example, we've got two flows that are within that 100-year regime. It's more useful for understanding the relative magnitude of a flood than for predicting exactly how often an event will occur. And then the retrospective simulation is the same as the forecast, except it's in the past. So this actually provides very useful data for understanding how a river has changed over time, when some of the peak flows might have been. It's useful for understanding. You can see this river that we're looking at has a very clear annual cycle where it goes from high to low. That's a very useful thing to understand. This retrospective can also be used to determine like a daily average flows for the same example. And you can see, yep, generally through the year, we've got a little bit of peaking in July, and then it really hits its max in the end of October, beginning of November. So if something is, you know, you can generally expect that this is what's going to happen and plan on that. But, you know, there will be variations year to year. You can also compute over the whole retrospective averages for the months, which kind of shows the same patterns, or the average annual stream flow. So you can see wet years, dry years, and create trends of what's going on. So I'm going to now see if we can pivot, and we're going to go look at the GeoGlows Hydro Viewer. Did that share pivot okay? Are we seeing the Hydro viewer?
Looks good.
Yes, Lyle.
Okay, excellent. So the GeoGlows Hydro viewer provides real-time information. This is the beta version for version 2. You can see we've got information on every stream in the world. They're all modeled, and you can zoom into any area. You can see the resolution coming up. So the area we're going to look at a little bit is the same area that Sheldon discussed in his presentation, right here in the Mississippi River. You can see, you can click on this. It'll load up the forecasts. Let's start with the forecast that we talked about. And it, is now getting the results for right now, what's going on. So it'll load that in just a second.
You can go ahead and talk about the retrospective and then come back when the forecast
Okay.
loads.
While that loads, we'll look at the retrospective data. So this is a history of the flow for the last, since 1940 on, based on the weather data that was observed. The forecast is done loading. As we talked about, you can see the daily average stream flow. So it's got a peak, around May, drops off every year. Seeing the same pattern down here. And you can see how it's changed over years, some really wet years, some really dry years. Just looking at the years, you can see pretty clearly that 2019 was a very wet year, which is the same year that we had the atmospheric river that Sheldon was discussing. If we would like to zoom in a little bit closer, we can zoom in and look at specific chunks. Oh, should come back up. Click the wrong button there. Let's reset the axes here. And we can see in 2019, as the atmospheric river gets going, that we start to get a lot of water down the river, which did cause some flooding. And I believe we will be seeing a map of that flooding a little bit later on. In terms of forecasts, oh, it's reloading it now because I clicked off. It'll be coming in just a second. Okay, we can see right now that the flow is kind of dropping off, and then it'll be peaking again soon. We can see all of the different ensemble members. They all agree coming up, and then as time goes on, they get a little bit closer. Now, to understand this right now, this number kind of seems a little abstract. We can turn on the return periods and see right now that really the flow is quite low. So in terms of flooding, we don't need to be worried about that right now. But if we were to go to a different spot, perhaps down in Mexico, where they've just been hit by a tropical storm, you'd see some of these forecasts coming up into these higher return periods, showing that they're at a greater risk of flooding. And so that's the Hydro viewer. It updates daily with the new forecasts, and there's an animation that kind of shows you how flow moves over time. That in the version 1 is working, in this beta version is not quite functional. So we're going to go ahead and hop back to, let's see if I get this to be on the right screen again on the PowerPoint. I'm sure someone will let me know if that's not right. So this we're not going to have a discussion, but we can all think about what does having access to this sort of information mean? If you don't have it, what problems can you have? And if you did have it, what problems could you solve with either the 80-year historical simulation or with the 15-day forecast? And we're going to look at one example of flooding that's occurred recently. So in Dubai. So this is the retrospective for a site near the Dubai airport. We can see that generally speaking, it's very dry in Dubai. And every once in a while, there's been these huge flooding events that can take you off guard. So we're going to look at a recent event and how this forecast can help you make life-saving decisions in real life scenarios. So the scenario is we're all going to imagine that we are engaged in the emergency response decision-making process in Dubai. Your job is to determine, what should be done, where should it be done, how best can resources be deployed. And then we're going to look through the forecast and the information that was available running up to this thing. So the first step, kind of like we did before, we find a river ID. We're going to be looking at this river ID right here. Near this river ID, you can see there's a lot of industrial areas. There's an international airport. There's the city of Dubai. These are all locations that, if there's a big flood coming down, are going to be impacted and have damages and potentially loss of life, because this is such a densely populated area. So this is the date's April 7th, and our forecast has just come in, and you can see the 15 days forecast. All of a sudden, a lot of the ensembles are starting to pick up a spike. They're starting to forecast, hey, something is coming. The good news is a lot of these are showing a spike, in about 2 weeks. So you've got almost 2 weeks to act. What can you do at this point? What would you choose to do, if anything? You've got 2 weeks. There's a lot of choices that are open to you in terms of, well, maybe looking at the areas, maybe getting some sandbags ready, maybe thinking about looking at the impacts, maybe trying to generate a flood map of this area, which will be discussed later in the session. And then as time goes on, the forecast, more of the ensembles are starting to pick this up and show that it's going to be a big problem. You still got time. As that decision maker, what are you going to do now in this situation? We can see, there's uncertainty. The median's starting to pick up. The upper bounds are really, really high. As a decision maker, what are you going to do with this forecast? What can you do now? 2 days later, there's still quite a lot. April 10th, it's still coming in. 11th, okay, some of the ensembles are starting to drop a little bit, but the median is still raising quite a bit. We can see maybe now it's breaking out into 2 different spikes, and it's continuing. Now we can see the median's way up. What actions can you take? How might you react? April 13th, everything's really starting to show that it's going. Some of the ensembles have dropped down on April 14th. The 15th, they're picking back up. As this first peak is now becoming a larger problem, the second peak is diminishing. And it's, a lot of them are saying it's going to be big. So this is kind of, now it's April 15th. You've got 2 days. You've had 2 weeks. So hopefully you've made good choices. And let's see now what the result of this flooding was. So in April of 2024, this flood actually happened. Those are all the real forecasts we've been looking at. They got record-breaking rain over the 16th and smashed a whole bunch of their records. They were severely affected, getting a year's worth of rain in just 12 hours. Floodwaters rose rapidly. You can see people are just out walking in flooded roads. Even days after the flood, satellites were able to pick up this flood from space. It was very severe. The Dubai International Airport experienced big disruptions. It was flooded, it created delays, which, having your airport out also cuts a lot of other things that are going on, decreases visitation, impacts the country's economy. And so you can see how understanding this flood ahead of time, with 2 weeks, there's a lot that could be done to mitigate the impacts, to get people out and to save lives, keep the economy running. And so that's why it's important to understand these impacts. We get these numbers, these flow numbers, but it's important that we understand that it's not just an amount of water, but that really it's a flood map. And it's important to take this number to make it into something that can be understood, which is the importance of flood maps, which there's a lot of different methods that you can take this flow and you can understand the impacts. There's topographic methods like hand, height above nearest drainage, and auto route that fill up areas based on the amount of water that's going to come. They kind of fill it up like a bathtub, give you a very rough extent. There's hydraulic models that translate that flow to the map by representing physics and physical processes like mass and momentum, and are able to give you a more accurate map that, but it's more computation time as well. And then there's also satellite methods, which will be discussed, how you can translate, that flow into a map using the observed satellite images. And so by understanding the forecast, by being able to couple it with flood mapping, you're able to provide something that, instead of just being a number of cubic meters of water that's coming down a river, actually shows the exact areas that will be affected by the flood and enable decision makers to make informed decisions, hopefully saving lives and mitigating impacts along the way. So with that, we'll take time for questions.
Thanks, Lyle. Great job, great presentation. And I see some questions coming up, and I'm going to help Lyle answer a few of the questions. Might actually share my screen for just a minute, just to demonstrate or show, answer a couple of those questions. One of them was, can we measure the accuracy to the forecasting model of GeoGlow's HydroViewer? And the answer to that is that you have the data yourself, so you can download that. In order to measure the accuracy, you need to know an observed flood hydrograph, and so that you can measure it against what was predicted by the model. Now that's difficult because it's hard to get data in every, it's expensive and difficult to collect data. That's why part of the reason we use models. But I'm going to share my screen and talk about another part of GeoGlows that Lyle didn't mention, but is available. And so let's see, we call this bias correction. So this is part of the activities that we've been involved in, and that is where we have data, we can correct it with that local information. And so you can see the area in red indicates not a great match between simulated and observed, but when we correct the bias by comparing the frequency of the simulated runoff with the frequency of the observed, we can match that and adjust the simulated or model data to be close to the observed. And after we do that, you see the part on the right that's is bias corrected and improved. And so that's also a part that will shortly be available in version 2, because we've done this for over 20,000 stations globally, and then we can extend that to ungauged rivers through machine learning by comparing the characteristics of the watershed and the characteristics of runoff, we can actually improve on every one of the 7 million rivers based on the information that we do have. And we're working with the WMO in order to get additional observed data, which will further improve it. And that points to the example that Lyle gave about the Google Earth imagery, that in time, this global forecast is going to improve for everybody around the globe. So that's one thing that I wanted to answer. Somebody brought up the point of the atmospheric river, and was that a part of what happened in Derna, Libya last September? And I just wanted to point out that while I don't know if this was an atmospheric river, it likely was, but Sheldon could probably go and look at that and say. I will say that this is something that's part of the GeoGLO's global forecast. And so here, part of the problem was they had a couple of dams that were upstream on some dry wadis that lead into the city of Derna. And so if you go into the GeoGLO's Hydro Viewer, you would have seen the information that Lyle has talked about. Here's the historical simulation. And you can see that a really large flow had only occurred once before, and was about 17, 18 cubic meters per second, so under 20. And for most of the rest of the period, there just was not a large flow. So if you looked at the forecast, however, in the days leading up, almost a week before, most of the ensembles were beginning to see very high flows, like way above 20 cubic meters per second. And then 2 to 3 days before, they could have had a higher certainty that something large was going to come down the river. Now, that would not have prevented the high flows. It probably likely would not have prevented the catastrophic failure of the dams that had caused additional flooding, but they could have been more prepared in the city with evacuations and understood that that was going to happen. So that's just part of the answers to the questions that you're given. I also wanted to point out that if you go to the version 1 Hydro Viewer, here you'll see the animated maps that Lyle talked about. This is the final part of version 2 that's coming in, but somebody asked, is this available in Central America? And of course, it is. It's available in the entire globe. And so you can experiment with that in the version 1 at apps.geoglos.org. You can also use the version 2, the beta version. It doesn't have the animated maps. It loads a little bit slower because of the mapping service that's being used, but it's available over the entire globe, but now at a resolution of 7 million rivers. So it models them out to about 30 square kilometers on average globally. So we can look at a couple of other questions. We have 5 or 10 minutes more. Be happy to answer. And somebody asked, is there the percent error in the forecast? Again, it varies, but by using the bias correction, we're able to bias correct the largely what is bias in the simulated precipitation or the forcing in order to match what happens on the ground and give a reasonable degree of certainty or comfort in using that information. One of the questions was, can we get inundation data from the Hydro Viewer? I guess let me show that really quickly, and but this will also lead into Amir Hussain's presentation. But in the version 1 viewer, you might notice that the VIIRS imagery can be turned on, and of course you can look for the help on this, and it will explain what these color bands are in the VIIRS imagery. This is NOAA's satellite that helps us use floods, and this is in real time, or what's happened in daily averages over the last period of time. So you can see in this area where there is some events that are shown up by the yellow and the pink and orange in the GeoGLOS forecast. We're also seeing more water on the ground. This is not forecasted, however, and what you're going to see in a few minutes when Amir Hossein presents, will be connecting the historical GeoGlow streamflow with historical data from satellite imagery so that we can then forecast from that what the satellite might see, or a synthetic satellite image of flooding. And so he'll be explaining that in his. So we don't see it directly as a forecast, but you can visualize ongoing what the VIR satellite is seeing as part of that. So that hopefully helps answer that question. Another question: who has access to develop apps on GeoGlows? Well, again, one of the places that you might go to is geoglows.org. Here you can become involved with GeoGlows. Because there are Python libraries that also provide access so that you can get this information through Python. You can then, anybody has the possibility of developing apps from the GeoGlows data. Now, whether or not they get posted as an app on our website would be different, but we'd be happy to collaborate and work with anybody developing those kinds of things. That's why it's set up as an open source model, so that we can use the community to develop different applications and resources. So is the accuracy of the model dependent on location? And yes, it is. It's dependent there. And again, the biggest part of the accuracy is at the actual precipitation forecasts that come. And the global model from ECMWF has different biases in different parts. And further, then the bias correction is the more data we have in those locations, the more accurate we can make the forecast by doing that bias correction. And that's why we encourage others to be able to share their observed data so that we can improve it going forward. It asks, the one question is, what's your success percentage? You can check it in retro every day. You get good results. Again, we've done a lot of checking in terms of, does it see the event or not? And it's highly accurate. There are a lot of different studies that have been done, both by ECMWF and others who've used that, as well as ourselves. And you'll find publications for that work on our geoglows.org site. The SWAT model was not used for flood mapping. We use different methods. Lyle mentioned some of them. Some are based on topography, just a bathtub filling up. Others are based on hydraulic models. And again, in a minute, you're going to see a presentation where they're based on predictions from satellite imagery. And then last question, or another question here: can we use GeoGlows data for flood mitigation measure design? Was the presenter or anyone on the panel has been involved in such a project could share his experience in terms of confidence on applicability? Would be great if a link such could be shared. So I will share in the chat window a couple of links when we're done here. One will be on stories.geoglows.org, where you can view the success stories of different places in applying GeoGlows, many of which are flood forecasting. And I'll link a few other sites where you can get publications that will also demonstrate some of that. The historical data, which can be downloaded from retrospective, is observed data or simulated data or generated. Currently, it is simulated data. Shortly in version 2, it will be bias corrected simulated data. If there's a station on there, it will be essentially the data from that station bias corrected. And even in the ungauged, using the machine learning, you will be able to download as part of the service the bias corrected. That's not there yet, but that will shortly be available. I will try to answer some of the other questions as we go, but for now, I would like to thank again Lyle, and you might provide a reaction for his great presentation. And then turn the time over to Amir Hussein, who will now take us to the next part of our our workshop, which will be looking at the flood mapping. So we've talked about atmospheric rivers and heavy rainfall. Then we've talked about using geoglows to predict the hydrology and where that water moves to in the rivers. And now we'll let Amir Hussein talk about work that he is doing at the University of Houston to predict where the flooding is and how that using satellite imagery translates into flood mapping. So go
Hey,
ahead,
Jim,
Amir.
would it be okay if we took a 5-10 minute break for our participants to kind of stretch their legs for a minute?
Absolutely. Thank you, Megan, for turn the time. Want to turn the time over again now to Amir Hussein Rostami and talk about how we can get to the flood maps. Go ahead, Amir.
Thank you, Dr. Nelson and Jim, Light Prince, for your great presentation. Let me share my screen.
We're seeing it actually.
Yeah, okay. Okay. Hello, everyone. My name is Amir Hussein Rostami. I'm a PhD student research assistant at the University of Houston. And our group works on flood forecasting method using the remote sensing techniques and dataset. So today I'm gonna talk about FEAR VIRS water fraction forecasting using geoglows that Lyle presented before and also National Water Model. You have lots of information now about the atmospheric river and the geoglows. Now they're gonna be connected together and see the final result of our session. So I'm sure that you have heard a lot about climate change, global warming terms in recent decades. So in this recent decades, the climate change has caused lots of extreme events such as flood. So in fact, the Earth's atmosphere now can hold more water vapor in the atmosphere. So we have seen more frequent and also more intense extreme floods. There are lots of examples. Just to show you some of them. The first one is Katrina hurricane in New Orleans, the Florence hurricane that happened in North and South Carolina, and also the April floods in Alabama and Florida. So these kind of floods, these kind of intense floods has caused lots of economic damages and life loss. So as a result, we need reliable flood forecasting systems, and also we need an accurate, scalable, fast, and also operational methods. Also, we need an inundation maps, not only for example, the stream flow forecast, because we want to know which area are affected by the flood. And it's very important for flood management and evacuation plans. So you know that the common ways of flood modeling, as Lyle presented, is hydraulic models or hydrodynamic models, but they need lots of computational resources, and it's very hard to calibrate those models. And also, they don't have the generalizability. For example, if you calibrate your model for a specific part, it's very hard to use that model in another part of the country or of the globe. So that was the primary motivation of our group to develop another approach, which is based on remote sensing satellite images. So what is FEAR? I'm gonna talk about FEAR in the next few slides. So FEAR stands for Forecasting Inundation Extent using Rotated Empirical Orthogonal Function Analysis. If you're interested, you can read these papers. I put it here. So the rotated empirical orthogonal function has the same concept of PCA, the principal component analysis. I'm gonna talk about the principles of fear to make it more clear for you. There are two important components in fear. The first one is the historical remote sensing satellite images, whether synthetic aperture radar, SAR images like Sentinel-1, or other kind of optical imageries such as Landsat or Sentinel, or in this study, we use the VIRS images. So we use the VIRS water fraction product, which demonstrate the percentage of a pixel that is covered by water. And this data is available from 2012 until now. So we have 12 years data set. This is the first component of fear. The second important component in fear is principal component analysis. So why we use PCA? If you're familiar with remote sensing area, remote sensing researchers, you know that it's a common way to for dimension reduction. But why we need a dimension reduction in our dataset? For example, imagine that you want to use Sentinel-1 images. Each scene of Sentinel-1 images needs around 1 gigabyte of memory. So imagine that you're working with a time series. You have, for example, 100 Sentinel-1 images, but lots of informations, lots of that images are not useful for us. We don't need all of those informations for our purpose. So by using PCA, we are gonna capture the maximum information in our data set, and also reduce the number of the dimension of our data set. In another word, the PCA can give us a simpler visualization of our complex data set. It's a good example here. You can see, for example, in another area, for example, we have a hyperspectral images. Hyperspectral images has, for example, 300 spectral bands, but we don't need all of them. So we use PCA and just select 3 of PCA modes to capture the most valuable information from our data set. In another word, we can say that it's representative of our data set, of our large data set. So how PCA works? There are some steps that PCA does. So the first step is calculating the covariance matrix of our dataset. So as you know, we see a remote sensing satellite image as a matrix. So we have lots of matrices, and we can calculate the covariance matrix. Note that the covariance matrix is something like this, and the diagonal elements are variance, and the other components are covariance. So this is the first step. And after that, in the second step, we calculate the eigenvalues and associated eigenvectors. But how we do that? We do this task with singular value decomposition. This term is very important in fear. So it means that we are decomposing our cube of dataset in 2 parts. The first part is the spatial modes or spatial patterns, because we are working with satellite images. We are working with spatial domains. We are working with pixels. And the second part is the temporal pattern, how they have changed during the time. After that, after calculating the eigenvalues and the eigenvectors, we will sort the eigenvectors based on the magnitude of eigenvalues. The magnitude of eigenvalues demonstrate the maximum variance. And it's another important keyword in fear. So what's the meaning of the maximum variance? Variance means change. So the maximum variance is showing the maximum change during the time. For example, imagine that you want to classify satellite images, for example, here. This is 1 pixel and 2 pixels. Okay. This pixel is water, and this pixel is vegetation or soil. What is important for us? The change between the spectral features of water and soil is important for us. So PCA can reveal this change. This is one of the reasons we used PCA to decompose our image. And at the end of the PCA workflow, it projects the data points on those vectors. Which vectors? The eigenvectors. So in another word, we can say that PCA is a kind of transformation from the XYZ, from the pixel spaces to the eigenvector space. For example, imagine that this is your coordinate system. This is X, this is Y, and this is Z. So by using PCA, you are transforming your data set to another space. But in this time is not X, it's eigenvectors number 1, eigenvectors number 2, 3, and whatever you have. So we are transforming our data to the directions with maximum variance, which means with max that can depict the maximum change in our data set. And you can see here, this is an example of singular value decomposition. This is the eigenvalues, this sigma, and this is the eigenvectors. So this is why we have used PCA in FEAR. But the question is that how FEAR works. So as Lyle mentioned, we need a translation from high stream flow, the high value of the stream flow, high runoff, in our satellite images, how we can detect the flood signals in satellite images. So we know that there is a meaningful relationship between hydrological variables. In this case, we are talking more about stream flow and inundation extent. So imagine that we have a flooding in our region. So what will happen on the satellite images? So in the satellite image, you will see the pixels that are covered by water. So when the stream flow increase, the number of pixels that are inundated will increase. This is a relationship. So by using the FEAR, by using our method, we are decomposing the cube of satellite images in 2 parts, as I said before, the temporal patterns or temporal modes and spatial modes. The temporal modes are based on eigenvalues, and the spatial modes are based on eigenvectors that access in that coordinate system that I told you before. So, for example, it will be the spatial mode 1, spatial mode 2, 3, and whatever is detected is the result of REOF analysis. So the temporal patterns are a 1D, one-dimensional result. So this is, for example, the temporal pattern. So we built a regression model between the hydrological data, historical hydrological data, and the extracted temporal patterns that from satellite imagery, from the VIRS water fraction. So imagine that this is the temporal pattern, and also we have, for example, stream flow. We built a regression model between these 2 kind of data sets. So what will happen in the future? This is where we are connected to GeoGLOS with National Water Model. For forecast, for the future, for forecasting, we need forecast hydrological data. So how that hydrologic data, for example, a stream flow can affect the remote sensing imagery, we get that with using the regression analysis that I told you before here. And after that, in the last step, we synthesized again our satellite imagery using the PCA that we used. So this is the overall workflow of FEAR, we used, as I told you, we used VIRS water fraction images. We implemented the PCA analysis, and we decomposed this satellite image in two parts: spatial modes and temporal modes. So note that the spatial patterns or spatial modes are static. They are constant, but the temporal patterns are dynamic. I mean, for the future, we get the forecast data, and we will update the temporal patterns. So we built the regression model between temporal and historical river streamflow that we get from USGS stations, built the regression models. But for the future, for the forecasting, we use National Water Model or GeoGLOS here, and we will forecast the temporal patterns. At the last step, as I presented here, in the last step, we will project the data points on the eigenvectors, or we are doing the synthesize. That's here in the flowchart. So this is the overall flowchart, overall workflow of FEAR. But I will show you the details of each steps in the next few slides. But before that, I'm gonna introduce our region of interest, our study area. We considered Mississippi River Basin near New Madrid. Here is Memphis, and here is the Mississippi River in the upper part of Memphis. And these are the locations of USGS stations. So for building the model, we used satellite, the VIRS water fraction from 2012 to 2023. And also we used historical streamflow data from USGS stations. These are the stations, station numbers, station IDs. After building the model for forecasting, we use National Water Model and also GeoGLOS, the retrospective data set of GeoGLOS. These are the reach IDs that are associated with these USGS numbers, USGS stations. So this area, the Mississippi River, is one of the most flood-prone regions in the United States. And we have seen lots of flooding, especially the record-breaking flooding in March 2019. And I will show you the flood maps in the next few slides. So let's go to FEAR and talk about FEAR, but step by step. So the first step is gathering and pre-processing the data set. As I said before, we use VIRS with water fraction data. You can access to VIRS water fraction data using, you have two options. The first option is using Google Earth Engine, and used the XEE package in Python. And you know, the XEE package is an array extension for Google Earth Engine. And another way is to download manually the dataset from JPSS Amazon Web Service portal. I highly recommend this method because it's more easy, and also it's very simple. And you can ingest directly from the Google Earth Engine a high amount of dataset. So, but we need also the pre-processing step. We keep only VIRS images with cloud coverage less than 5%. You know that because the cloud coverage is a huge obstacle in optical images. So we wanted to make sure of quality of our model. So we select an strict threshold, just 5%. And also we crop our images based on the region of interest shapefile. You can see here the shapefile and the output of cropping the satellite images based on our shapefile. And another thing that should be noted is that the VIRS data has also other classes, for example, snow, ice, land. But because we are focusing on flood, and the only important thing is for us is water fraction, water. So we removed all of those classes from the satellite images. This is before pre-processing and this is after pre-processing. You can see that here the range of the values are from 0 to 200, but because we have removed all of those classes, we just have 0 to 100. That shows the water fraction in each pixel of satellite imagery, of VIRS images. And please note that this satellite image has the spatial resolution of 375. So the next step is to is the significant test. So as I said before, we are decomposing the satellite, the cube of satellite images in two parts, temporal and spatial modes. But we want to know that which spatial and temporal modes are significant. In another word, which spatial modes represent the most dominant change over the ROI, over our region of interest. Because remember our purpose. We want to use, for example, from 10,000 images, we want to use only, for example, 100 of them as a representative of the whole data set. So for that purpose, we use the Monte Carlo simulation. Using the Monte Carlo simulation, it's a shuffle selection of VIRS water fraction pixels and calculating the eigenvectors. And the output of this step is the number of modes that are significant. Here is the output. You can see this is the eigenvectors and this is the number of modes. So the orange ones, the orange plot, the orange line, that is lower than the blue lines are significant modes here. So this is the second step. So now we know which modes are significant, which modes can represent our dataset in the best way. The next step, the step 3 and 4 are together. This is the main step of FEAR, implementing the rotated empirical or REOF analysis, or PCA. So in this way, we are going to find that in which direction our dataset has the highest value of variance, we are going to find the direction with most change. This is the result of a REOF analysis. You can see here, for example, this area, the reddish pixels are demonstrating the historically inundated areas. So what does it mean? It means that these pixels in this mode are representing the highest change over the time, from 2012 to 2023, over this area. But because we have used water fraction dataset, this change means the change in water fraction. What phenomenon can change the water fraction? So the most important one is flood. As you can see here, the main stream river here is as 0, is white. It means that it didn't have lots of change during the time period that I mentioned. So because this is the permanent water, it's not inundation. It's a permanent water and it's not related to flood. So this mode, these two modes are representing the inundation areas. You can see here, and not mode number 4 is representing the inundations here. You can see the reddish pixels, and what is it's very important to know that each modes represent different areas that are historically inundated. So you can see that mode number 5 that is detected, that is recognized as a significant mode, represents and shows the inundation in tributaries, not in the mainstream, despite all of these modes. And it's associated with this USGS station. This is a USGS ID number. So at the same time, so this is the spatial mode. But we also talked about the temporal modes, the temporal patterns. The blue lines are the temporal patterns, and the orange line is the USGS streamflow, observed streamflow, not simulated. So this is the real data. We can see that there is a good correlation. There is a good match between the temporal patterns and the streamflows from USGS. And we just, because in this area, for example, we have 3 or 4 or 5 USGS stations. But which stations we have used? Those stations that have the highest correlation with our temporal patterns that extracted from satellite imageries. So this step 4 and 3 are done together, and we selected those stations with the highest correlation coefficient, because we wanted to make sure that this, for example, stream flow is related to the flood, and this is the flood signal. So after extracting the spatial modes and temporal patterns, the next step is to build the regression model. So we are gonna make a connection between the hydrologic data, the forecast hydrologic data, with our temporal pattern. So what is this question mark is a regression model to create this relationship between them. So whatever regression model you can use, but it depends on your case. In our case study, we use the deep neural network. You can use whatever you want. For example, a polynomial and simple machine learning models, support vector machine, random forest, whatever you want. But what is important here is to build that relation here. You can see that the x-axis is USGS stream flow, and the y-axis is temporal modes. After building this relationship, these regressions, so at the end, we want to know what will happen in the future. This is where we need the forecast data. For forecast data, we relied on GeoGLOS and also National Water Model. As Dr. Nelson and Lyle presented, that GeoGLOS is a global model. You can have the access to forecast stream flow all over the world, but National Water Model is only for the United States. So we both of them for forecasting hydrologic data here. Here the regression model is built. Now we for the final step, we need to synthesize the water fraction images. So so far we have decomposed our satellite images. This is a cube, not only one image, lots of images, to 2 parts, spatial and temporal pattern. So we built the regression model here from using the historical stream flow and temporal patterns that we get the historical hydrologic data from USGS. Now, the input of our model will be the forecast hydrologic data from GeoGLOS and National Water Model. So we will have the forecast temporal pattern, the forecast temporal modes using the forecast hydrologic data. And if we multiply the if we multiply the spatial modes with temporal patterns, with temporal modes, we can synthesize it. Here is the formula of synthesizing the image. For example, as an example, if we multiply, it's a dot multiply. It means the projection. The spatial mode number 1 project or dot multiply with temporal pattern number 1 plus a spatial mode number 2 dot multiply temporal pattern number 2, and so on. And also we have added a temporal mean to keep the overall pattern of our image. It's a temporal mean of all of the pixels in the time of period. So what will be the result? The result is a synthesized image. It's not a real image. It is synthesized by FEAR. So this is the way we have synthesized the various water fractions, and we will forecast the inundation maps. And there is the last step here is just performing the quantile scale mapping. This step is needed because after, as I told you before, after these multiplies, the range of the data set will be different. It's not from 0 to 100. The original data set is water fraction from 0 to 100, but because we have done some multiplies and some mathematic operations, it becomes higher than 100. So we calculated the cumulative distribution function of original data set, and we scaled our synthesized pixels to the same range of values. This is not a very important step, but it is needed because we wanted to have a forecast, a synthesized image in the same range. So this is the steps of FEAR. And in the next slide, I'm going to show you the results of FEAR water fraction forecasting using GeoGlows and National Water Model. So as Sheldon and Lyle presented and mentioned, we have observed an extreme flood in March 2019 in the Mississippi River. This is the observed VIRS water fraction data. This is our pseudo nowcast because it's observation. This is why we called it nowcast. But these are the simulation, the forecast. We use the result of the output of these models, the National Water Model and the GeoGlows. And you can see here, this is the inundation map that we can say that it's a good match between them and also the real data set. Also in different dates, for example, 10 March 2019, although it is covered by cloud in the real images, but because we are synthesizing, we don't have cloud here. We can overcome this issue, the cloud issue, by synthesizing the image. You can see here that the GeoGlows is a better match with the real data set in this day. The other days, you can see that due to the cloud, is almost covered by the cloud. You cannot see anything in the real images, but we have synthesized the flood inundation maps using FEAR and also using the hydrologic forecast data, GeoGlows, National Water Model in these 2 days, 7 and 9 March. You can see the result here. Another example for 11 March, it's almost cloudy, but synthesized. But please note that because we are using the output of the models, they can have some underestimation or overestimation. As Dr. Nelson mentioned, these models, these hydrological models output needs to be bias corrected. So you might see some underestimation, for example, here in National Water Model or in other kind of data set you're going to use. And the last slides that the result of FEAR output for April and May 2019, you can see again the real images and our synthesized flood inundation map using GeoGlows and some maybe some overestimation here and underestimation in GeoGlows or overestimation in National Water Model. If you're interested, you can go through our website. This is a web app that we have developed at the University of Houston. I will show you some examples from this app. You can just put your region of interest and select the National Water Model configuration you want, and you can get the final inundation map. thank you for your attention. But if I have the time, I would like to show you the Python code of our sphere. Let me just. And share my screen. Yes. I don't know how to. Okay. Dr. Nelson, can you see my screen?
Yes.
Okay, just a quick overview of the Python code of of FEAR. So the first one is just installing the required packages because it might take a long time. I just ran the code before the session, so I'm not gonna run these cells again. So you should install the required packages, import those packages to use in future, and also you need to mount your Google Colab with your Google Drive, and also if you want to use the Google Earth Engine, you should authenticate your project, your Google Earth Engine project here. For example, this is the name of my project and it needs some authentication. So just for your visualization purpose, this is the VIRS dataset. Here, yes, you can see. This is the water fraction. This is the main, the permanent water, the river, and these are the water fractions of these images. And so this function is preparing. This is the first step I mentioned in the presentation for preparing our dataset. Remove the cloud, remove the other classes, crop our images. It's a function to do that. The second function is to do the significant test using the Monte Carlo simulation. Here is the code. And the next one is the REOF analysis. This is the main part of FEAR, doing the PCA, extracting the temporal patterns, the spatial patterns, spatial modes. And so this function, finding modes that related to flood, is related to that part that I mentioned about the correlation analysis between the USGS streamflow time series and the temporal pattern. Just to show you, and these are the functions we leverage to. For example, we wanted to have the match dates in our data because we are using different kind of data set. We want to just find the match dates. These are the auxiliary functions, just a plotter function to visualize the data set. This is the core function that we get the the spatial and temporal patterns and get the forecast data to synthesize the images. You can use this function, and also the regression model. As I told you before, we use the TensorFlow deep neural network to build the regression. And another one is the quantile scale mapping that I explained. This is a function we provided for quantile scale mapping. This is a function for getting the USGS data, because you just need to put your shapefile and it detects the number of and the location and the number of the USGS stations inside your shapefile, and also preparing the National Water Model forecast. Just for visualization, your shapefile, your region of interest. This is the Mississippi River shapefile. Here is for loading and processing the data, the pre-processing the data. It might take a few seconds. Just in the meanwhile, let me explain the other functions. By using this function, we can you should just put your starting and ending date. It will get the USGS stations data, and it's run. And I have, as I told you, I have already run this part because it can take a few minutes. So this is the output of significant test that I showed you. And that is the final output of real analysis, the temporal patterns. You can see here the blue ones, the orange ones is the USGS stream flows, mode number 1. This is the affected area by the flood in the spatial modes, mode number 2, mode number 3, mode number 4, and mode number 5. So another step that we have done is that, okay, we have now 5 modes, but after that we built the regression model with these modes here. Yeah, the x-axis is USGS stream flow and the y-axis is temporal patterns. But we have an accuracy criteria, the NSE accuracy criteria, but just we used the modes that have the threshold that satisfy the threshold of NSE equal to 0.6, just higher than. So we use 3 modes to build this regression models. And after that, this is for synthesizing image. This function is for synthesizing the image using the USGS stations. I just run this, and this is an example. You can see here, the first one is our synthesized based on historical water stream flow, and this is the real data set. So another step that you should take for using the national water model or GeoGLOS is to detect and recognize that which reach ID is associated with your USGS stations. For doing that purpose, fortunately, GeoGLOS has provided, for example, if you just put your latitude, the latitude and longitude of your USGS station, you can find the reach ID of that that is associated with that USGS station. But for national water model, you should do it manually. For example, here, let me show you. Yeah, you can just find your reach ID by click on that, and you can get the reach ID. And excuse me. Yes. So these are the reach IDs that are associated for our USGS stations, National Water Model and GeoGLOS. And this is for preparing National Water Model data, but because it's gonna take time, I just load and load those data sets. For GeoGLOS, you can use instructions here. I used this instruction to get the data set. It was very easy to just programmatically get the data set for your region of interest and detect the reach ID. And after doing all of them, the last part is forecasting. So for forecasting, you have 3 options. The synthesized type could be using National Water Model or GeoGLOS. It's incorporated in our function. And just you need to put your starting date and the end date for forecasting. I've already done this part, and I'm gonna show you just the final result here. Just you can change the time, your time of interest. If you run this part, yes, you can see here the output of VIRS image, using USGS, using National Water Model or GeoGLOS, or you can just simply change this, for example, 10, and run the code and see the final result. That's it. If you have any question, I would be happy to answer that.
Great presentation, Amir Hossein. I don't know if you can bring up the Q&A. We have maybe 5 minutes to answer a couple of questions from there, and then maybe you can finish
Okay.
answering those you don't get to. And then I'll take just a minute and wrap things up.
Mhm. Okay, let me just see some of those questions. Mhm. The first question is that does VIRS has same accuracy and in day and nighttime and also in any weather condition? And is it specific to FEAR method or we can use any other remote sensing data? So, the water fraction is a product of VIRS. It's not a raw VIRS images that they have used the daytime images to produce that water fraction product. And for FEAR, as I said, as I presented in the first few slides, we have also implemented FEAR with Sentinel-1 images in the Mekong River, but unfortunately, I don't have enough time to present that. But you can read that papers. We also used Sentinel-1 images, the SAR images, but there is a very important difference because in VIRS water fraction, we are working with only a product that is related to water. But when you are going to use Sentinel-1, is not only water, is backscatter of the SAR images. So you need another step. You need to take another step. That step is water mapping. We on that project we used Z-score water mapping. So just just for you to note that you should consider that. Another question, do these models consider variation across temporal and spatial scales? I'm not sure that I understood this question well, but yes, the the PCA is kind of it's a pattern recognition. So it can consider the change that happened during the time. So will a precipitate descent, does the FEAR whatever has a global data set? I think yes, the VIRS water fraction has a global data set. One of the most important feature in VIRS VIRS images, they have a large tile and you can download the data set. But in the Google Earth engine, I think we have only the VIRS water fraction for the United States, as far as I know, in the Google Earth engine. But in the JPSS, the Amazon Web Service portal, we can access to all of those VIRS water fraction for all over the world. And I think we don't have any other questions.
Okay. Well, thank you again. Let's give Amir Hossein a virtual appreciation for his great presentation. And I hope that you have been able to appreciate the connection between in our presentation today between going from large forecasted river events, or I'm sorry, atmospheric rivers and precipitation to hydrologic response, and then being able to use that in order to develop a flood map, which is what we need in order to understand who and where the flooding is occurring. I'm going to want to thank everybody involved in today, specifically Sheldon and Lyle and Amir Hossein for their great presentations. And there is a short survey. I believe you'll be emailed the survey, but also you can, using the QR code, you could scan that and go and fill out the survey directly from there. And so look forward to next one will be in 2 days. So in fact, I'll go back here on June 27th using AI to predict convective weather hazards. And so I hope that you'll be back to join us for that. Thanks again, and we wish you all well.